Okay, second video on the DHSS model. An abundant resource, costly to extract. And this is also a special case which isn't the main normal case analysed in the model. That it's not the case like the DHS&S set up and played with in 74. Okay, so what is it? It's a case where we still have this investment loop, but now, and we still have the production function, and we still have savings, and we still have labor, but, yeah, and we still have these equations. I gotta sneeze. Or maybe not. But we also send some of our product, y, we send, so this is I, we send some of it to I, some of it to C, but some of it to X. And X is extraction. I'm not going to try and draw a coal truck here. X is extraction effort. So this product, whatever it is, remember we had hammers in the solid model, whatever it is, you can either keep it back in the factories, you can send it to the extraction sector, or you can consume it. One way of thinking about it is to call it a widget and then say that widgets can quickly and easily be converted into different things. Consumption goods, investment goods, or extraction goods. So the tricky thing is producing these all-purpose widgets, which can then be at zero cost transformed into different kinds of goods. Okay, and given an input X of widgets into here, the output R is phi X. Or phi if you like, phi I call it. So this is a linear production function, yeah? Just a nice, straightforward, constant returns production function. Double inputs, double output. So phi is a kind of productivity, isn't it? So this is super straightforward, but we need to adapt these equations, don't we? So we can define this actually in different ways, but I choose to define it like this. It depends really how we think about S. But effectively here, contrary to the picture, I'm sort of stripping off the X first, and then we save a fraction S of what's left after taking out X, which is Sy minus X. And we consume the fraction 1 minus S of Y minus X. You could also define it where you take off the investment first, and then, yeah, it would be slightly different, but it would all work out the same. Okay, the properties of the model would be the same. Okay. Solve for the growth rates on a BGP. Okay, and I'm going to do this super fast. Or I'm going to try anyway, because it's exactly the same method as I just did on the previous slide when I took it really slow. Okay. So yeah, I would strongly recommend you actually just stop the video here and try and do this for yourselves. Yeah, that would be really good. But anyway, I guess you've restarted the video now, so here we go. So we assume a balanced growth path, so k dot over k is constant on a BGP, so or you could say, but k dot over k is S y over k minus delta, therefore y dot over y equals k dot over k. So we know that, and then you could say, if you like, again, but y dot over y is, and now I'm going to go straight away that L is constant and R is constant. And it turns out, once you've got the hang of this, you can just, it's fine to just write down the answer, okay? So these exponents turn into pre-multipliers of the variables, and then the variables are put into dot growth form. So y dot over y is 1 minus alpha minus beta times, and L is constant, L is constant, so it's 1 minus alpha minus beta times AL dot over AL, which is G, plus alpha K dot over K, but now R is no longer constant, is it? So we need plus beta R dot over R. Okay. You're fine in exam and so on to do straight to this, but only do it if you're totally confident, yeah? If you're not confident, work through the steps, yeah? But then once you've worked through the steps a few times, hopefully you'll be happy just to write this down. Okay, so now using y dot over y equals k dot over k, we have 1 minus alpha y dot over y equals, so I've put y dot over y here and taken it over, and then we have 1 minus alpha minus beta g plus beta r dot over r. So y dot over y is, and of course 1 minus alpha minus beta over 1 minus alpha, we can write it if we like as 1 minus beta over 1 minus alpha, just to emphasize that it's less than 1, plus beta over 1 minus alpha r dot over r. Okay, so that's pretty cool, isn't it? But what's r dot over r? Let me just pause the video and take stock how I'm going to explain this. Okay, I'm back. Yeah, I realised I got here and I was like, I think I might have done something wrong. And I have done something wrong, yeah? Because this isn't actually right, is it? Because this is not right. So I need to go back here. This is all fine. So don't worry here. But I need to redo this. Because actually we've got k dot is s y minus x minus delta k. K dot over k is constant on the BGP, but k dot over k is s y dot over y minus x dot over x minus delta. So for balance, not only does k dot over k have to be equal to y dot over y, but x dot over x has to be equal to y dot over y too. You could see it intuitively here. Like if x is growing at a different rate compared to y, then this can't be balanced, right? If x is growing faster, that means we're siphoning off a bigger and bigger proportion of production to the extraction sector over time, which can't lead to balance. Yeah. So for balance, x, I, and c all have to grow at equal rates. Otherwise it's not balanced, is it? Okay, so we know that x dot over x is growing at the same rate as y dot over y. But from this, again using this technique, if r equals phi x, and you can do this the long way like I showed you in the previous video, but I'm just going to write r dot over r equals x dot over x. Yeah, if r grows by 1%, x is going to grow by 1%. So we can add r dot over r to this. So r dot over r is also equal to y dot over y. So let me wipe this, because this is just unnecessary and confusing. So this is also equal to y dot over y. So then we have 1 minus alpha minus beta y dot over y equals, oh, I'm going to write it back to front because you know what I'm going to do next. G 1 minus alpha minus beta, right? So I've taken that over. So then of course we can cancel. And we're back to production growing at the growth rate of labour productivity. We don't have the growth penalty anymore that we had with the land. Why is that? I was going to say let's leave it to the study questions, but it's not in the study questions, so I'll just explain. Well, it's because R, with land R was fixed, so that made a drag on growth, because R wasn't growing and R was an input. But here R grows at the same rate as Y, at the same rate as K, at the same rate as C. There's no drag. Okay. So what do we see? We see exponential growth, exponential increase in resource extraction. And I wonder what we see for the resource price. And that, I think, is in the study questions. Let me just double check the study questions. Yep, so that's in the study questions. So you should work out, set up the profit maximization function for these guys, or the profit maximization problem for the representative producer here, and work out their demand function for R, and then given that R is increasing like this, what is going to happen to WR. Okay, and you should find something different. Okie doke. And one thing you could think about is which of these models, the land model or the resource model, fits the data. And of course the land model you would hope would fit the data on land, whether the resource model hopefully in the best case might fit the data on resources. So then we can say to that, do the two models fit the data? Have a think about that. Okay, we'll talk about that in the class, whatever we call it. Okay. Yeah, and I'm going to stop the video here because the next one is going to be quite a long one. That is the standard DHSS setup. We had land here, which was just exogenous, and there was no need for inputs. Then we had an infinite resource stock, so there's no scarcity here, but you need inputs to extract it. The third case we're going to look at is also a very special case. There's a finite resource stock, but it's free to extract, so there's no need for inputs. It's just you go and get it when you want it. But it's not open access. Okay, there's a market for this resource. Owners are deciding when to sell it and at what price. Okay, and that's the next case which I'm about to start on, but that is going to be the next video.